So this slide shows a heating curve for water from minus 25 degrees up to 125 degrees. And here we actually have numbers on the x-axis. This would be for heating 1 mole of water. It starts out as a solid, so you have an ice cube. And then to heat the ice cube, we add energy, right? Remember what the equation is? Q equals MCAT, MC delta T. So when we're changing the temperature of something, we can use the specific heat capacity and the temperature change to figure out how much energy is needed. So heating the ice from minus 25 to 0 would require 0.941 kilojoules for every mole of ice. Once you get to 0 degrees Celsius, now the ice begins to melt. There's no temperature change here, so you can't use Q equals MC delta T. Delta T is 0, that equation doesn't work. You use the heat of fusion here. The heat of fusion is given in kilojoules per mole generally. If we have a mole that we're melting, it's going to be 6.02 kilojoules of energy. Once it's all melted, the temperature starts to go up again, and we can use Q equals MC delta T to calculate how much energy is needed to heat it from 0 to 100 degrees. So the liquid warming up would require 7.52 kilojoules per mole, and that would be calculated using Q equals MC delta T. Once it begins to boil, again, the temperature is not going to change anymore. And so to calculate this amount of energy needed, we'd use the heat of vaporization, 40.7 kilojoules per mole. Once it's all vaporized and you continue heating it, the temperature will go up above 100. And here we're just going up to 125. And you would use Q equals MC delta T again with a specific heat capacity of water vapor. So that would require 0.904 kilojoules.
Steam can get hotter, but water stops.
Liquid water at atmospheric pressure cannot get above 100 degrees. But steam can go much higher. Mm-hmm.
And then the critical point is when it turns back to...
The critical point would need to happen at an elevated pressure as well, so it would have to be in a sealed container. Yeah. So any questions about this? We need to be able to do calculations like this, where you're given, an ice cube that weighs 50 grams and it's minus 75 degrees Celsius, and how much energy is needed to melt it and get it up to a temperature of 25 degrees Celsius. Things like that. The way to approach a problem like that is to sketch a heating curve. It's not really a curve because it's a series of lines. But you have temperature changes, and the equation for those is always Q equals MC delta T. And then you have flat places where the state is changing. The temperature where this happens depends on the substance. I do expect you to remember that water freezes at 0 and boils at 100. Other substances, I would not expect you to remember, and you'd be given the boiling point, the melting point. So use the heat of fusion here, Q equals MC delta T, heat of vaporization, Q equals MC delta T. So you figure out where you're starting, where you're ending up, and then for each line segment, you have an equation. You calculate the energy, and then you add them together. If you're cooling something down, it's the same process, except that the energy is going to be negative because it's being released. So here's an example. This example is actually what's shown on the previous slide. For good or bad, I don't know. Calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. So I'm just going to sketch a little heating curve down here where this is temperature and this is heat. And we've got ice, and so the ice is going to increase in temperature and get to a point where it melts, and then the water's going to heat up until it boils, and then the steam heats up.
I have a question.
Yeah.
What's the coldest you can get ice? Like, say you have ice, what's the coldest is absolute zero, right?
Right. The coldest is absolute zero, which I don't think has been actually attained, but
What
really
would happen
close.
to it? Would it
Well, at absolute zero, all molecular motion ceases. So they wouldn't be vibrating at all.
But it would still be
It'd still be ice. Mm-hmm.
Okay.
Still be ice. So how many segments you have just depends on how many state transitions you have. I'm going to identify these different temperatures. We're starting out at minus 25 because that's what the problem told me. And we're going up to plus 125, again, because that's what the problem is telling me. These flat places in the middle happen at the melting point and the boiling point. So this is 100 degrees, and this is 0. And that's all in Celsius. So I'm going to have 1, 2, 3, 4, 5 line segments. I'm going to give them letters because we've got enough numbers going on here. Call it A, B, C, D, and E. We're going to have an equation, a calculation for each of those.
Then sublimation would be a lot easier to calculate.
Well, sublimation would be easier because you could skip all that stuff in the middle, yeah. So for A, I have ice warming up. I have a temperature change, so I've got Q equals mc delta T. So I need the mass. Well, I was told this is 1 mole of water. So you'd use the molar mass, and that would be 18.02 grams. And then you need the specific heat capacity of ice. There's 3 specific heat capacities given here: steam, water, and ice. I'm going to use the ice one, 2.09. And that's joules per gram degrees Celsius. And then I have to figure out what the temperature change is. The temperature change is the final temperature minus the initial temperature. I guess I should put a unit on that. It ends at 0. It began at minus 25. So that's a positive change, right? $18.02 times 2.09 times 25. So that's going to give me 941.5 joules. The second segment is a horizontal line. That's just the ice melting. So I need the heat of fusion. I've got 1 mole of ice, and I'm going to multiply by the heat of fusion. 6.02 kilojoules per mole. Moles cancel out. And so that's going to be 6.02 kilojoules of energy to melt the ice. Line segment C is slanted. There's a temperature change there. Q equals mc delta T. Well, the mass of my water hasn't changed. I just melted it, that's all. But the specific heat capacity for liquid water is different than for solid. So I need to use this one. No, not that one. This one, 4.18.
Is that 941 point what?
5 joules. And then my temperature change Sometimes people get mixed up and they'll use this whole range as the temperature change. You just want the particular line segment that you're looking at. So here for line segment C, you're starting at 0 and you're going to 100. So final minus initial, 100 minus 0 is 100. And so that's giving me 7532 joules. Line segment D, we're vaporizing the water. 1 mole of water times the heat of vaporization, 40.7 kilojoules per mole. So that's 40.7 kilojoules. And the last line segment, the steam, is heating up. So again, Q equals MC delta T. The mass is still the same. Mass doesn't change when you heat stuff up. The volume changes, but the mass doesn't. I need the specific heat capacity of steam, 2.01 joules per gram degrees Celsius. And now the temperature change. I was told in the problem that my final temperature is 125. But for this line segment, we started at 100. So the temperature change is the final temperature minus the initial temperature, which is 25 degrees Celsius again. And so that's going to be 905.5 joules. To find the total amount of heat, I need to add these together, but I've got some that are in joules and some that are in kilojoules. So we need to have all the units the same because you can't add apples and oranges. So I'm going to convert this to kilojoules. So that's going to be 0.9415 kilojoules. This one's already kilojoules. Converting this one would be 7.532 kilojoules. That one's already in kilojoules, and then converting this one, 0.9055 kilojoules. And I'm going to add those up. So 0.9415 plus 6.02 plus 7.532 plus 40.7 plus 0.9055. And I'm getting 56.099 kilojoules. Considering significant figures, these had 3 each, and I underlined the digit, and so when I'm adding, this is the 3rd decimal place, this one's in the 2nd decimal place, this one is in the 3rd decimal place, this one is in the 1st decimal place, right? And then there's the 2nd. So our total should end in the 1st decimal place, and so we should round that to 56.1. Any questions? There are lots and lots and lots and lots of different kinds of problems that could be asked. So identify where you're starting on this stair-step thing, where you're ending up, and then a separate calculation for each line segment. How much heat would be released if I took a mole of steam at 125 degrees Celsius and changed it into ice at minus 25 degrees Celsius? Negative 56.1 kilojoules. The same amount of heat would be released.
Go from steam to ice?
If we go the other way, if we go from here to there, it's the same number, just a different sign. So if you're doing something cooling off, minus signs, no matter how good you are at math, minus signs can be problematic, right? If you don't include all of them, things get all messed up. It's much easier thinking about warming something up and having everything be positive. So if you want to calculate a cooling, what I would do is I'd calculate the warming and then just change the sign at the very end. And that way you don't have to worry about all the negatives. Yeah.
So when that made me think about the fields, right, with the
Mhm.
ice, because you're putting that energy out when you're freezing, trying to freeze the ice. Does that do more than setting up fires and trying to blow heat across the ground?
The question is flooding the field more effective than having burners or fires or something?
Because they do that too sometimes.
They do that as well. I can't say for certain whether the fires are more effective. Now, if you had a space heater for each tree, that certainly would be very effective, but it would also be very expensive and inefficient. And so flooding the fields works good enough, and it doesn't require a lot of resources, doesn't create a lot of pollution, and so it's just cheaper and easier. Yeah.